Today, we're diving into the story of a technology so powerful it could literally change the world. A technology that was almost dead on arrival, and the two brilliant ideas that pulled it back from the brink of impossibility. Just think about it for a second. Imagine a machine that could design brand new medicines in a matter of days, not decades, or one that could create codes that are truly uncrackable, or even simulate the very beginnings of our universe. I mean, that's the incredible promise of quantum computing. But all of that immense power comes with an equally immense vulnerability.
And here it is, the catch, the devastating paradox at the very heart of the quantum dream. The exact same thing that makes these computers so unbelievably powerful also makes them impossibly fragile. We're talking about a single stray photon, a tiny vibration in the room, anything at all, bringing the entire massive calculation crashing down to zero. This wasn't just a bug, you see. It felt like a fundamental flaw in the universe. So you have to wonder, right? What made these theoretical machines so powerful and yet so fragile? Well, to get that, we need to look at the very heart of any computer, the bit.
Okay, so your phone, your laptop, they all run on classical bits. They're basically just simple, reliable switches. They're either on or off, a 0 or a 1. Super straightforward. A quantum bit, or a qubit, is, well, it's a completely different beast. Thanks to a wild property called superposition, it can be a 0, a 1, or kind of a blend of both at the exact same time. Now, this ability to exist in multiple states at once is where the quantum computer gets all its incredible power. But it's also the source of its greatest weakness, because that delicate, both-at-once state is ridiculously fragile.
And that brings us to the main villain of our story, decoherence. Peter Shor, in his 1995 paper, put it perfectly. He said, "This is when a qubit gets entangled with the environment, thus in effect collapsing the state of the quantum computer." You can think of it like the universe is eavesdropping on your calculation. The split second it looks, that fragile superposition is just gone. Your qubit is forced to pick a side, 0 or 1, and poof, your entire computation is ruined.
This right here was the checkmate, the ultimate catch-22 that made so many scientists believe a big, useful quantum computer was flat out impossible. I mean, in a normal computer, you just read a bit to see if it's messed up. Easy. But with a qubit, the very act of reading it is what messes it up. You literally can't check for an error without causing one. So how on earth do you solve a problem you're not even allowed to look at?
For years, the whole field was pretty much stuck on that question. Then, in 1995, a researcher at AT&T Bell Labs named Peter Shor published a paper that changed, well, everything. He figured out a way to look at the error without actually looking at the data. The core of his idea was deceptively simple, something taken right out of the playbook for normal computers. If you want to protect a piece of information, what do? You make copies of it, you create redundancy. But this immediately raises a huge problem. You see, one of the fundamental laws of quantum mechanics says you cannot perfectly copy an unknown quantum state. So how do you make backups for something you can't even clone?
Shor's brilliant answer was this number, 9. To protect one precious, fragile, logical qubit of information, he proposed using a team of 9 tougher physical qubits to act as a kind of quantum bodyguard.
Now, Shor's genius was realizing you don't copy the qubit's value itself. No. Instead, you spread its information across all 9 of those physical qubits, linking their fates together through a process called entanglement. So think of it this way. The information no longer lives inside any single qubit. It lives in the shared collective state of the whole team. So now, if some random error comes along and flips one of them, the other 8 still hold the group's secret. They can perform a kind of quantum majority vote to find the one that's out of line and fix the error, all without ever destroying that original precious information.
And you know, this quote from Shor's paper just perfectly captures the magic trick he pulled off. You're not measuring the data, you're not looking at the secret, you're measuring the symptom of the error. You're measuring the disagreement within the group. You're basically asking the team, hey, does everyone here agree? If the answer is no, you know an error happened, and you know how to fix it. And just like that, the original superposition is restored.
And this just shows you how effective it is. So, let's say the probability of a single qubit failing is some number p. Well, the probability of 2 qubits in that 9-qubit team failing is proportional to p squared. And if p is already a small number, then p squared is a much, much smaller number. Shor's code didn't just slightly reduce the error rate, it absolutely crushed it. For the first time, it made long, complex quantum calculations seem mathematically possible.
Shor's breakthrough really opens the floodgates. I mean, he proved it could be done, but his method was just the first step. The next huge leap forward came from a physicist at Oxford University, who took Shor's specific trick and turned it into a universal toolkit for everyone.
This physicist, Andrew Steane, he realized that this wasn't just some clever one-off solution. He saw that the problem was deeply connected to the classical theory of error-correcting codes. You know, the same kind of math that makes sure your phone calls are clear and your computer files don't get corrupted. By building that bridge, he created a general framework, an instruction manual for building all sorts of powerful quantum error codes.
So let's just put them side by side. Shor's code was absolutely revolutionary, but you could say it was a bit of a brute force approach, right? 9 qubits to protect 1. Steane, by borrowing more sophisticated ideas from classical codes, developed a method that was way more efficient, using just 7 qubits, and also far more powerful. It was able to correct a much wider variety of potential errors. And if you look here, this figure comes directly from Steane's paper, and it's basically the circuit diagram for a quantum spell checker. It's a visual map of a process that checks for errors, figures out what kind of error it is, and then applies the exact right correction, all while the main computation just keeps on chugging along, completely unaware that anything even happened.
So, the work of Shor and Steane did so much more than just offer a clever fix. It provided a mathematical guarantee. It was proof that a reliable, fault-tolerant quantum computer wasn't just some sci-fi fantasy, but a real engineering possibility.
And this is the payoff. This graph, also from Steane's paper, is the blueprint. Now, it might look a little academic, but trust me, this is one of the most important charts in the entire history of quantum computing. It's the map that shows the path from an impossible dream to a concrete engineering challenge.
So what is this really showing us? Well, in essence, it proves something called a threshold theorem. It says that if our engineers can just build physical qubits that are good enough, meaning their error rate is below a certain critical tipping point, then we can use these error-correcting codes to create logical qubits that are virtually perfect. We can drive the final error rate as close to zero as we want. And just like that, building a quantum computer wasn't a fight against the fundamental laws of physics anymore. It became an engineering challenge. Get your hardware to that threshold.
Okay, so let's bring it all together. What did these incredible theoretical breakthroughs from the mid-90s actually give us in the end? They gave us so much more than just an error fix. They gave us a recipe for creating a protected, isolated subspace, a kind of quantum sanctuary where these delicate calculations could unfold, completely shielded from the noisy, messy outside world. They found a way to let quantum mechanics do its incredible magic without the universe constantly peeking over its shoulder and spoiling the trick.
That fundamental barrier had been broken. The path forward was finally clear. The work of Shor and Steane transformed quantum computing from a theoretical curiosity into a tangible, achievable reality, one that companies and governments are now pouring billions of dollars into building. And it leaves us with one thrilling question to think about. Now that we have the tools, what impossible things are we going to choose to do?